Hi, welcome to the next lecture on heat and mass transfer. Today we will focus on mass transfer and see what we can learn from the previous lecture on heat transfer. In the Spark of this week we have seen that stirring helps tremendously when dissolving a substance in, for instance, water. Why is that? How could we describe this? In the present lecture we will see that it's all about driving forces and mass transfer coefficients. When stirring, the mass transfer coefficient goes up drastically. And that speeds up dissolving by orders of magnitude. Try it yourself. Put sugar in your cup of tea and don't stir. Guess what will happen? In the previous lecture, we have seen that heat transfer is present as soon as there is a driving temperature difference. In the case of conduction, Fourier's law describes how much heat is transported. However, in general, heat is not only transferred by conduction, but also by convection. We use that when we blow on hot food to cool it down quicker than just waiting. Newton's law is used to describe the relation between the driving temperature difference and the resulting heat flow. In a first approximation, we used that the heat flow is proportional to the driving temperature difference and to the area through which the heat flows. Everything that is not captured by A times delta T is put in a heat transfer coefficient H. We further introduced the dimensionless Nusselt number that linked the first estimate of H, namely the steady state conduction through a flat plate, to the true value of H. In today's lecture, we will look at mass transfer. In principle, we should develop a new theoretical scheme. However, there is a strong similarity between heat transfer on the one side and mass transfer on the other side. This can be understood if we look at the different ways mass can be transported. Like with heat flow, we know from practice that the driving concentration difference in a species gives rise to transport of that species. And like with heat transfer, we have identified two ways of transport: diffusion, which is equivalent to heat conduction, and convective transport. In the table, the general form of these two is given. If we compare them to the expressions we used for heat transfer, the similarity is striking. Convective heat transport is in both cases a volume flux times a concentration. In the case of heat, the concentration is ρ Cp times temperature, representing the internal energy. In case of mass transfer, it is the concentration of the species itself. Mathematically, these expressions are the same. Also for diffusion, via Fick's law, we have a description that is mathematically the same as for heat conduction via Fourier's law. Based on these observations, we can expect a strong similarity between heat and mass transfer, and indeed that is the case. Therefore, we proceed along lines similar to heat transfer and introduce the mass transfer flavor of Newton's cooling law. The mass flow is proportional to the driving force times the area times a mass transfer coefficient K. We can make this dimensionless by using for K as a first estimate the result for steady state diffusion through a layer that is stagnant. The difference between the true K and this first estimate is given by the Sherwood number, abbreviating as SH. So, if we look at the mass transfer table, we see that the mass transfer coefficient K has units meter per second. The higher the K, the higher the mass flows for a given driving concentration. Again, we can use an analogy with Ohm's law by interpreting 1 over K as a resistance. Now to mass transport. Look up the previous lecture on heat transfer and you will see that everything we said on Ohm's law and heat transfer can directly be translated to mass transfer. Note that in the equation relating K to the Sherwood number, we have to be precise in our writing. The d in the numerator is the diffusion coefficient. The d in the denominator, on the other hand, is the size of the object. This is easy to remember. A large diffusion coefficient, we expect a large mass flow and thus a large K. On the other hand, if the layer through which the diffusion takes place is thick, the diffusion is slow. Hence, the flow must be inversely proportional to the size of the object. Mass transfer can be pretty annoying. Take for example this piece of lovely French cheese. If you wrap it in a bag and put it in your fridge, the next day everything in your fridge will smell like it. Mass transfer can go through bags, even though we might think they are airtight. If we use our analogy to diffusion through a stagnant layer, we can copy the entire analysis from the steady state heat conduction through a flat plate. We found there that the temperature profile was a straight line, resulting in H equals lambda over d, the thickness of the plate. We could summarize this by stating Nusselt is 1. The analogy tells us that also in the diffusion case, the concentration profile must be a straight line. Pushing the analysis further, we would find that the mass transfer coefficient K is then equal to the diffusion coefficient, italic d, over the object thickness, straight d. Also, this result can be summarized. Sherwood is 1. Here is an example of potential diffusion through a thin layer of plastic. These candies are wrapped in plastic, and we may think that everything is contained inside. However, if you would have the nose of a dog, you would easily pick up the smell from the candies through the plastics. Dogs don't have the problems picking up the very low concentration from the candy that have diffused into the room. No wonder dogs are used at airports to sniff for drugs. The analogy goes on. Take a hot sphere that is cooling down via conduction. We found Nusselt is 2. We can anticipate that the same will hold for diffusion from a sphere into its surrounding. We indeed get Sherwood is 2. However, the analogy doesn't mean that a cooling sphere and a slowly dissolving sphere are in all respects the same. Let's check this via an example. First, we analyze a sphere that is cooling down. We take as case that the resistance to heat transport is completely outside the sphere. Then it follows that there can be no temperature difference inside the sphere, since, like with Ohm's law, a driving temperature difference over a zero resistance would cause an infinite current. Thus, we conclude that in the present case, the sphere, while cooling down, is at a uniform temperature. To find the cooling down, we set up an unsteady heat balance with the sphere itself as the control volume. As always, we start with the general form of the balance and go over it term by term. The present case is unsteady. The sphere is cooling down. Thus, the left-hand side is non-zero. It actually keeps track of the loss of thermal energy in the sphere. This energy is given by the volume of the sphere times the product of the density and the specific heat times the actual temperature of the sphere, T sub S. On the right-hand side, we first have the in term, which is 0. No heat is flowing into our sphere, as it's hotter than its surroundings. Also, the production term is 0, as there is nothing internally inside the sphere that produces heat. Finally, we consider the outflow, which is non-zero. The sphere is cooling down. We start by describing this via Newton's cooling law. The next step is to further specify the heat transfer coefficient H and connecting it to Nusselt. Finally, for this situation, a sphere cooling down via conduction, we can use Nusselt is 2. In principle, this has only been shown to be adequate for steady-state situations. However, it turns out that pretty quickly after the start of the cooling process, Nusselt is 2 also holds for further cooling of the sphere. So we write down the heat balance. Note that the driving force is the temperature of the sphere minus the temperature of the surroundings far away from the sphere. As the sphere cools down, the driving force will become smaller and smaller. Thus, the heat flow out of the sphere gets smaller and smaller as well, and the cooling slows down, exactly as we know from experience. The term in front of the driving force on the right-hand side, shown in the yellow box, contains only constants. To make the structure of our equation easier to read, we will call it alpha. Thus, we can simplify the equation for the change of the temperature of the sphere to ddt sub s equals minus alpha times Ts minus T far away. This equation can be solved by separation of variables as is shown. The general solution of this equation is that the natural logarithm of the temperature difference is equal to minus alpha times T plus an integration constant. This constant can be found from the initial condition of the sphere. That is, at T equals 0, the sphere had a temperature T sub S0, which is some given number that we in this example do not further specify. Combining the initial condition with the general equation allows us to find the integration constant C. Now we can write down the solution of our problem, which you see on the sheet. The temperature of the sphere decreases as an exponential function of time. Indeed, from this solution we can see that the cooling down of the sphere goes slower and slower.